Now coming to the second type of fault, which is line to line fault. As the name indicates, there is a fault between the two lines. So here there are three phases R, Y and B. So in which I have considered there is a fault between the phase Y and phase B, and the fault impedance is being represented by ZF. And if you observe, the fault current is nothing but the current which is flowing here, so through this, which is equal to IY, and IB flows like this, which is opposite to this fault current. That's why it is represented by minus IB. So this is the representation of the fault current. IF is equal to IY or minus IB when there is a fault occurred on between phase Y and phase B. So under fault conditions, as I've told, IF is equal to IY is equal to IB, or we can either write another way, that is IB equal to minus IY, and the current flowing through the phase R, IR, is equal to 0. And coming to the potential difference across this ZF, so this point I can take it as VYN and this point as VBN, or simply VY and VB. The potential difference across this VY minus VB or VYN minus VBN is equal to the impedance ZF into the fault current IF, or it is IY. And we know the relation, the sequence currents is given by 1 by 3 times this matrix into IR plus IY plus IB. But IR, it is 0, IY is there, representing IB in terms of IY. So IY is equal to minus times IB. So here it is represented by minus IY. So from the first row we get this first zero sequence current I0. I0 equal to 1 by 3 times 0 plus 1 time IY minus IY. So this gets cancelled and we will be left out with 0. Now coming to the positive sequence current I1, so it is written as 1 by 3 times 1 into 0 plus A into IY plus A square into minus IY. So that is written here. So when I take IY common, I will get 1 by 3 times A minus A square into IY. Similarly, when I write equation for I2, I2 is equal to 1 by 3 times 1 into 0 plus A square into IY minus A into IY. So here I am going to get minus 1 by 3 times A minus A square into IY. Sorry, it is IY. I have written IB. And what is the phase current? It is the sum of the zero sequence, positive sequence and negative sequence currents. And we know that IR is 0. So I0 plus I1 plus I2 equal to 0. And again here I0 we have obtained it as 0. So when you substitute that, we are going to get this relation I1 is equal to minus of I2. And from this matrix, where the phase voltages are being represented by this particular matrix into V0, V1, V2. So from this equation, I can write Vyn, which is nothing but Vy, as 1 into V0 plus A square into V1 plus A into V2. And similarly Vb as 1 into V0 plus A into V1 plus A square into V2. So these values are substituted in this equation, and again I1 will be represented as 1 times I0 plus A square times I1 plus A times I2. So after substituting that, I am going to get this relation like this. Now taking on simplifying this equation, this V0 gets cancelled, and taking V1 V2 terms common, and again on the right hand side, since I0 equal to 0 and I2 equal to minus I1, when I am going to substitute that, so on both sides I am going to get A square minus A term common, so which can be cancelled, and will be left out with V1 minus V2 is equal to ZF times I1. because this A square minus A gets cancelled. Since I naught equal to 0, that is the 0 sequence current is 0, the negative sequence network acts as a dead network. So we are not going to have this particular negative sequence network when there is a line to line fault. This should be noted. Okay. So in other words, I can say that in line to line fault there is no term which is ground. If there is a ground, then only the zero sequence network or the zero sequence components come into picture. So here, since there is no ground, we are not going to make use of this negative sequence network, and it acts as a dead network. Now from these relations we have obtained initially IR equal to 0, I2 equal to minus times I1, or we can also write it as I1 equal to minus I2, and V1 minus V2 equal to ZF times I1. So making use of these three relations, we are going to form an interconnected sequence network. See, before the fault, as I have said earlier, the three networks, the positive sequence, negative sequence and the zero sequence network, these three are independent to each other. But when there is a fault, now the combination of these networks comes into picture. Coming to the LL fault, we need not worry about the negative sequence network, but based upon this relation we can obtain the interconnected sequence network with the positive sequence and negative sequence network. So if you observe, this is the positive sequence network and this is the negative sequence network. The potential difference, so if you observe here, this is the node voltage V1, here node voltage V2. V1 minus V2 equal to ZF times, and the current flowing through this is I1. So based on these relations, we have drawn the interconnected sequence network for LL fault. Now from the network, if you observe, V1 is nothing but Vf minus Z1 I1, and similarly V2 equal to minus I2 Z2. So substituting these values here in this equation, we will obtain Vf as I1 times Z1 plus Z2 plus Zf. So we will make use of the before relations also. So V1 equal to I1 times Z1 plus Z2 plus Zf. Now from this I can obtain I1 as Vf by Z1 yes. Now here I can obtain I1 as Vf by Z1 plus Z2 plus Zf, which is equal to minus I2, and I0 equal to 0. The fault current If is equal to Iy. Iy can be written as I0 plus A square I1 plus A I2, and we know that I0 equal to 0, and again I2 equal to minus times I1. So from this relation, A square minus A times I1. We will be finding out this value A square minus A. We know that A value is minus 0.5 plus J 0.866, and coming to A square, it is the complex conjugate of this term. So we are going to get minus 0.5 minus J 0.866. So on simplifying this, we are going to get minus J root 3. So substituting back in the relation, that is If is equal to A square minus A value is minus J times root 3 into, and what is I1 value? I1 value is this which we have obtained earlier, Vf by Z1 plus Z2 plus Zf, that is being substituted here. So finally the fault current is given by minus J times root 3 Vf by Z1 plus Z2 plus Zf. And if you want to get the magnitude of the fault current in LL fault, so we will be getting root 3 times Vf by Z1 plus Z2 plus Zf. So this is how we obtain the fault current in double line fault or LL fault. So this is the second type of fault, which is a short circuit fault observed in unsymmetrical fault analysis.